Welcome to my talk for AQuest 2020. My name is Justin Yirka. I'll be talking about our recent work, Qubit-efficient entanglement spectroscopy using qubit resets. It's now available in the archive. This is joint work between myself and Yiğit Subaşı, who's pictured here. I'll begin by summarizing the main contributions in our paper. First, we designed new NISQ-ready algorithms for entanglement spectroscopy. This task can be thought of as given many copies of a quantum state on subsystems A and B, and a parameter n, estimate the trace of the nth power of the reduced density matrix rho A. The key feature of our new algorithms is that they require asymptotically fewer qubits than any previous efficient algorithm, while still remaining similarly noise resilient. This means they enable spectroscopy of larger quantum systems on NISQ devices than previously possible. The key tool that we use to achieve this is qubit resets, and we test our algorithms using both numerical simulations and on Honeywell's quantum computer. Our second main contribution is to define effective circuit depth to both explain our results, and we think that this will be a useful tool in assessing the noise resilience of future circuits which use qubit resets. At a high level, the goal of entanglement spectroscopy is to understand the entanglement structure of some quantum system. For example, a quantum state may be the output of some simulation which we wish to learn some property of. In particular, we're interested in bipartite quantum states across subsystems A and B. In this case, the entanglement structure is fully characterized by the eigenvalues of the reduced state, rho A, where we trace out subsystem B. Importantly, learning the entire set of eigenvalues yields more information than learning just the entropy alone. And learning about the bipartite entanglement is important for physical applications such as understanding the topological order, phase transitions, or whether a system obeys area laws, among others. To formalize the broad application of entanglement spectroscopy, we let the problem be given as input some integer n, and given black box access to a circuit preparing a pure state on subsystems A and B, estimate the trace of the nth power of the reduced density matrix rho on subsystem A. Now this is a slightly restricted model in which we only consider black box access to a circuit. Some previous work in the literature have considered different models. Now, importantly, the first few traces, meaning the first several values of n, are often sufficient to reconstruct the largest few eigenvalues of the reduced density matrix. And those largest few eigenvalues are often sufficient for learning physical properties, including for the applications listed on the previous slide. In the literature, there's often been an alternation between discussing trace rho to the n and finding the nth Rényi entropy. This is because they're effectively equivalent in that finding one gives you the other via this formula here. There are previous algorithms for entanglement spectroscopy, computing trace rho to the n. Two known efficient NISQ-friendly algorithms that I'll focus on in this talk are first HT and TCT. I'll focus more on the second algorithm because it gives us the better results, but I'll begin by introducing HT as a means of introducing some interesting ideas. First, to introduce HT, recall the swap test, which is the Hadamard test, but with a swap operator and copies of two quantum states. Now, when those two states are set equal to each other, the swap test gives state overlap, which becomes trace rho squared. Now, this algorithm was generalized by Jory, Steiger, and Troyer, where instead of using the swap operator, they use the cyclic permutation operator, P, on many copies of the state in order to compute trace rho to the n. And so this algorithm, illustrated at the bottom, illustrates that the expectation value against the permutation operator is useful for computing trace rho to the n. Now, to introduce TCT, first note that the Bell basis is an eigenbasis of the swap operator. And recall that a Bell basis measurement is a fairly simple measurement. It's illustrated here. It's a C0 gate, a Hadamard gate, and some classical post-processing. And combining these two observations, first Garcia-Escartin and Chamorro-Posada, and later rediscovered by Cincio, Subaşı, Sornberger, and Coles, realized that you can simulate the swap test and measure state overlap using just Bell basis measurements. More recently, this was applied to entanglement spectroscopy by Subaşı, Cincio, and Coles by measuring the state overlap via Bell basis measurements of n copies of a state with n permuted copies of a state. This gives you the squared expectation value, which is equal to the squared trace row to the n. And because the trace is real and non-negative, this gives us trace row to the n. Now this doesn't quite yet give us the TCT algorithm. First, we need a neat trick. So again, we're using Bell basis measurements to measure the overlap of n copies of psi and n permuted copies of psi. And the neat trick we can apply is to perform the permutation operator without using any gates. All we have to do is we can re-index the C0 gates and re-index our post-processing formula. This is shown in the figure on the right. And what we get is that because all of the C0 gates act on different qubits, we have a single layer of C0 gates, we have a single layer of Hadamard gates, and we have a constant depth circuit. This is the TCT algorithm. This brings us to our new algorithms, which we refer to as qubit-efficient. Given that the state is 2k qubits, both HT and TCT require a number of qubits that's linear in n and in the size of the state. We give variants of both HT and TCT, which require a number of qubits linear only in the size of the state. The number of qubits is independent of n. That's an asymptotic improvement. Now the seam and cost of our new low width circuits is that our circuits have a larger depth than the original ones. But we use qubit resets to avoid the usual noisy effects of this larger depth, and so beat the usual trade-off between depth and width. So at this point, I'll talk a little bit about qubit resets. We usually think of resetting a quantum circuit back to their zero state at the beginning and end of a computation. But more recently, various quantum computing companies are rolling out a feature called intermediate measurement and reset. This is the ability to first measure a qubit individually and then reset it, driving it back to its zero state in about a time comparable to a measurement. At that point, we can reuse those qubits. We think that qubit resets are an underexplored tool that are going to be crucial in the NISQ era, as long as qubits are limited. And we've only seen a few algorithms which take advantage of this. So here we give just one of our algorithms. Due to the constraints of time, I'm only going to cover the qubit-efficient TCT. We cover TCT instead of HT because it gives better performance. And this is actually the slightly wider version of TCT. We have one which uses fewer qubits, but it's slightly more convoluted. So in this diagram, every time a new zero state is depicted, that means a qubit reset. And you can make a quick check between the original TCT and the qubit-efficient TCT, and note that in both cases, each copy of psi only interacts with up to 2 other copies. And this leads us to the key intuition that when a register finishes its interactions with the other copies, that register has no more work to be done. We can then measure that register, reset it, and reuse it to load a new copy. And we can repeat that as necessary. This is what allows us to compute trace row to the n using a number of qubits totally independent of n. We tested both our new algorithms and the previous algorithms in order to compare their noise resilience. We first did this using noisy simulations. At a high level, for each value of n, we ran each algorithm on several different input states with varying degrees of entanglement. And then we compared the slopes of the true values of trace row to the n to the estimated values. So ideally, a slope of 1 would be achieved. And then we plotted those slopes here. So again, an ideal result would have a horizontal line at 1.0, and the results here are degraded due to noise. The key takeaway is that there's almost no difference between the original algorithms and their qubit-efficient variants. So here we have two groups of HT and TCT, where there's almost no difference between the original TCT and the qubit-efficient TCT, and similarly for the HT group. This means that we get our asymptotic savings in the number of qubits while suffering almost no degradation in terms of noise resilience. We also tested our qubit-efficient algorithms on Honeywell's 6-qubit ion trap quantum computer. We ran the qubit-efficient TCT with 3 different states of varying entanglement on n=2 up to n=7. It's notable that the original TCT would have required 28 qubits to accomplish this, more than the 6 qubits available. And this is indicative of the fact that our qubit-efficient algorithms should enable spectroscopy of larger quantum systems than previously possible. The results are in the plot here, and although there's deviation between the ideal results, the solid lines, and the experimental results in the dashed lines, I'll note that all of the experimental results are ranked in the correct order from most entangled states to least entangled states. Now I'll introduce our second main contribution, which is to define effective circuit depth. Circuit depth has been interesting generally for one of 2 reasons. In complexity theory, we're able to prove things about classes of bounded depth circuits like AC0, QNC0, etc. But more practically, it's a good heuristic for the susceptibility of a circuit to noise. Basically, the deeper a circuit is, the more likely that noise will dominate. However, in the case of circuits which use qubit resets, depth is no longer a good predictor of noise resilience. The evidence for this claim are the circuits I introduced in this talk. For example, the original TCT had constant depth. The qubit-efficient TCT had depth more than linear in n. I'm hiding some factors here. This is an asymptotic difference, but they perform similarly in the presence of noise. Depth is no longer a good heuristic for predicting noise resilience. We'd like a heuristic which can predict the noise resilience of circuits, even when those circuits are using qubit resets. However, defining such a measure is a non-trivial task. We can come up with counterexamples of circuits which seem to reset every qubit frequently, and yet there's information flow from the beginning of the circuit all the way to the end of the circuit. Now that I've shown that this is a non-trivial task, let me give you our definition. Define effective circuit depth to be the maximum length of a path along which there is information flow. Then, for both the original TCT and the qubit-efficient TCT, the effective depth is constant. You can see this in the diagram below. This explains the results in our work, that both algorithms have similar effective depth, and so they have similar noise resilience. Importantly, effective depth reduces to standard depth for circuits which don't use qubit resets. And so there's no need to switch between definitions based on the setting. We think that effective depth should be useful for rating the noise resilience of circuits in the future, both with and without qubit resets. Finally, I'll summarize my talk. So again, this was on our recent work, Qubit-efficient entanglement spectroscopy using qubit resets, now available on the archive. This was joint work between myself, Justin Yirka, and Yiğit Subaşı. Our first main contribution was that we introduced new algorithms for entanglement spectroscopy via estimating trace of rho to the n, which use asymptotically fewer qubits than previous algorithms, but achieve similar noise resilience. This enables spectroscopy of larger quantum systems on NISQ devices than previously possible. And second, we define effective circuit depth, both to explain our results analytically, and which we think will be useful for assessing the noise resilience of future quantum circuits which use qubit resets. Lastly, I'll leave you with the open question of what other algorithms and applications can be made noise resilient, low width, and NISQ ready using qubit resets. Thank you.